While he's doing that, can you still hear me okay? Okay. I wanted to thank Channel Islands National Park for inviting me to give a talk to you here today. It's always great to come here. And we just got back from doing some field work on San Miguel Island, where one of our youngest most USGS members in Denver are old guys like me. But we have a few young people, and we took one of them today out to San Miguel Island to start some work. And so I've actually got some photographs that were taken just this last week. So try to convince you that we're right up to date on things here. But at any rate, it's a pleasure to be here, and I wanted to extend a special thanks to Dave Vagan and also to April, who kind of set this talk up for me. And great to be here again. What I'd like to talk about is something that has always kind of interested me, and is something that is special to the Channel Islands National Park, and that is that they are islands. And a question that I think is an interesting one is, when did they become islands? When did they achieve that island character? And what that really means is, when did they rise up out of the sea or fall from the sky? But it's more likely that they rose from the sea. So we're going to talk about that today, and how we go about answering that kind of question is part of what I'll be talking about. And I'll show you some of our results. I do have to warn you, a lot of these are kind of preliminary. We're still working on this. Sampling on Santa Cruz Island yesterday, specifically for the purpose of trying to add some more data to this. And so everything I'm going to be saying here is sort of a first approximation of what we now think is going on. And we'll learn more, and it could change as time goes on, so stay tuned. At any rate, let's go ahead and move along. And first, two very big thank yous. One to Channel Islands National Park. This is one of the most supportive national park systems I have ever worked in. Everybody here has just been wonderful to us for several years now of work. And we thank all of them for everything they've done. And then two natural resources programs of the U.S. Navy on San Nicolas and San Clemente Islands also want to thank. They have also been very, very helpful. And my San Clemente thank yous go all the way back to 1976 when I first started working out there. So thanks to everybody. We have never had a problem getting on an island if there was somebody in charge who had a way of getting us there. So it's a good group to be working with on any of these islands. So what is the importance of quaternary? And first of all, we'll start with the very first sentence with some terminology here. The quaternary is the most recent period of geologic time. And it's about the past 2.6 MA, and as you notice there's a little asterisk there. We'll be using this throughout this talk. MA simply means milloanno, or millions of years. So 2 MA is 2 million years. And KA is thousands of years. I don't think we've used that in this talk, but you'll see the term MA, and that just means millions of years. It's a shorthand that's commonly used. At any rate, what is the importance of quaternary, or last couple of million years, uplift rates on the California Channel Islands? Our primary question helps us determine when these islands became islands. But in addition to that, the rate of uplift of these islands actually is a reflection of the tectonic setting. Tectonic means internal earth processes, folding, faulting, that kind of thing. And that tectonic style is reflected in the rate of uplift in a lot of places. So it can tell us a lot about that. Uplift is a driver of geomorphic processes, and by geomorphic, what we mean is something related to the science of geomorphology, and that's the study of landforms. It's that part of geology and physical geography that has to do with the origins of the landscape we see. How are mountains formed? How are mountains shaped? How are valleys formed? And this kind of thing. Uplift is a driver for that. Creates potential energy that helps drive a lot of those processes. So it tells us a lot about that. It's important for biogeography, and particularly island geography. When these islands became islands, that sort of set the stage for a lot of our insular endemic species. And by endemic species, we mean those species that are limited in their distribution to the islands. And there are a lot of them on the Channel Islands, as there are on a lot of other islands. And when those islands became islands tells us how early that could have happened, how soon that could have happened. And if we have different times when islands popped up. That can tell us also how separate evolutionary pathways may have taken place over different time scales on those islands. So that's of interest. And an interesting one for global change studies, well, we're looking at a rising sea at present and in the very recent past. It's actually important to look at how we can measure this, and one of the best ways is with tide gauge records of historic sea level, but it requires knowledge of uplift rates. So this is one of the ways we can get a long-term baseline for how stable an area is, tectonically speaking, and that in turn helps us in historic tide gauge interpretations for what is currently a rising sea level that we're seeing now. We won't be talking much about this. We will be talking a lot about these other three things, and we'll proceed away here. So much of the California coast is affected by strike-slip faults whose movements are primarily horizontal. And the big one of them all, of course, is the San Andreas, which you can see right in through here. This is a great map that you can actually get online for free from the California Geological Survey. And these different colors are reflective of when the most recent documented evidence of movement is on there. The size of the lines is reflective of the kind of the importance of these, and so on. And I'm not going to go through all those color codes, but as any Californian knows, particularly any Southern Californian knows, we have lots of faults here in Southern California. But notice that most of them are more or less running parallel to the San Andreas fault here. And most of them are, in fact, strike-slip faults, and most of that movement is horizontal. However, no fault movement is purely horizontal. There's always a vertical component of uplift or downdrop. So in other words, when we talk about strike-slip faults, they're not primarily like the ones that we would refer to as normal faults, where there's an uplifted block and a down-drop block. Primarily the movement is horizontal, but there's a component of uplift and downdrop. So it's actually what geologists refer to as an oblique kind of slip or movement, where it's kind of moving diagonally, mostly horizontally, but sometimes a little bit of vertical component. So this is what creates a lot of our hills, valleys, and our islands as well. And you can see that a lot of faults run parallel to a lot of our islands. San Clemente Island down here has a big fault running parallel to it on its eastern side. San Nicolas has a series of faults on its eastern side as well. Here off Catalina, up here by Santa Barbara Island. And then we have some faults running east-west here in the northern Channel Islands as well. So we've got faults nearby, sometimes running through or adjacent to a lot of our islands. And this is what is creating a lot of the movement, tectonic movement, horizontal and vertical, that we see on our islands. But just keep in mind there is a vertical component as well as a horizontal one. Okay, so we're going to look at all of these islands, and as you can see, they're all 9 of them are shown here. Nobody objects to that? 9 islands? Okay, there are 9 islands. There are 8 islands that you know about, but there's actually a 9th island called the Palos Verdes Hills. Okay. Yeah, so there will be a quiz too. Just kidding. Anyway, at one time during the last interglacial period, which we'll talk more about in this talk, there was a shoreline over on the east side of the Palos Verdes Hills. The LA Basin, to a great extent, was under water. Okay, there's some people who would like to see that happen again. But at any rate, the Palos Verdes Hills during that last high sea level was an island. Okay, you can actually trace the shoreline all the way around that peninsula, or at least you could at one time. So we have 9 islands here, and we're going to talk about the Palos Verdes Hills as well as the other 8 that are still currently islands. Okay, including Channel Islands National Park, the top 4 here, and part of this Nature Conservancy territory, and Little Santa Barbara Island over here. Okay. Okay, our primary method of studying this rate of uplift and sea level history.
Just a clarification. You studied all 8 of the existing islands, is that correct?
Right.
And you're only going to talk about the northernmost Channel Island?
No, I'm going to talk about all 9, actually. Yeah. Actually, I'm going to talk about 8 of the 9, but including the 9th. not including the 8th, which is Catalina. And I'll talk a little bit more about that later. Well, you'll know why in a minute. There aren't any marine terraces there that we're sure about. That's the reason why. I know. We're disappointed. But at any rate, let's talk about this. Marine terraces are landforms that form in the surf zone as wave-cut benches. And here you see one, a modern one, in San Pedro. It's characterized by a sea cliff here, by a wave-cut bench. And this sea cliff retreats as the waves undercut it, particularly during wintertime storm waves. And so the bench expands in a landward direction as the cliff is undercut, and the sea cliff retreats back. And what is usually left behind during summertime, when you have less wave action, or during any quiet period at all, a pile of sand and gravel, and usually there are shells in there as well. And that's very significant for us, because that's the method by which we date these. So as you're going along, even a rocky shore like this one, you can usually find a few shells, or you can find evidence of where the shells have bored into it, like these bored holes in the piece of the Monterey Formation here. So this is a modern wave-cut bench, a sea cliff, the deposits that are left on it, and what I forgot to mention is the junction between the sea cliff and the wave-cut bench here is something we call the shoreline angle. And that is the best indicator to us of approximately where mean sea level is. Okay, pretty close to that. So when we're looking at uplifted marine terraces like this, we always try to find that shoreline angle, because that's our best indicator of where sea level was on that landform, not necessarily at that level, but on that landform at the time it formed. Okay, so reiterating this just in a simplified form, this is a diagram of what we're seeing, what we saw in the last picture, that sea cliff here, the present sea level, the modern wave-cut bench is right here, and the shoreline angle is that junction. And so present sea level is about where that shoreline angle is located. During the last interglacial period, we're presently in an interglacial. During the last one, which was about 120,000 years ago, sea level was about 6 meters higher than present, so it was up about here relative to what a modern bench would look like. So in that last photograph, sea level would have been up about here someplace had there been no uplift. It turns out it's the terrace that formed during that time period is way up there someplace, but we'll talk more about that in a minute. So that leads to the next part of this diagram, which is an uplifted terrace, is this feature that I've shown here. It's simply a wave-cut bench like this one, but one that's been uplifted. Still can retain a shoreline angle. It can still retain a sea cliff, but we call it a paleo sea cliff or an ancient sea cliff because it's no longer forming. And this is what we try to map. This is the elevation we try to measure. And the deposits on top of it are what we look for materials to date. Okay? So what we find throughout history, in the geologic sense of the term, geologic history and recent geologic history, is a series of cycles over the last 2.6 million years. Remember, we call that the Quaternary. That's the period of time where we have a series of ice ages, or glacials, and warm periods, or interglacials, cycling through over the last 2.5 or so million years. How many people have seen an inconvenient truth? Just about everybody. A lot of people anyway. Do you remember that graph that Al Gore shows where he actually has to get up on a step ladder to show where CO2 levels are relative to glacial interglacial history? That was a CO2, excuse me, a CO2 graph from an ice core in Antarctica. But this is a record of those same glacial interglacial cycles from deep sea cores. And this is time in thousands of years before present. So we're at time 0 here. We're currently in an interglacial. And this is kind of a sea level curve, if you will. Sea level is up at present right now, of course. During the last glacial period, when ice expanded, it was down here. And then it wobbled back and forth until we get to the last interglacial here, 120,000 years or so ago. And it was slightly higher than modern sea level. And then we had other interglacials in the past. Okay? Our marine terraces in California primarily are recording these interglacial periods because these were the periods when sea level was close to present, maybe a little bit below it, maybe a little bit above it, but relatively high. Okay? Now, the question is, did marine terraces form when sea level was low, way offshore? Indeed they did. And in fact, K.O. Emery found them in 1956 off California with some of the earliest offshore bathymetry that was done. He found terraces that he speculated dated to the last glacial period, and even dredged up some coralline algae, and it came out about 20,000 years, which is pretty close to right about there. So this is something we have known. However, when a block gets uplifted, if it formed way offshore and then gets submerged, it often doesn't survive over numerous glacial interglacial cycles. So the ones that do survive tend to be the ones that are recording our interglacial periods. Or in some cases, if the uplift rate is very low, it simply never gets very far away from that offshore position, high enough up to where we can actually see it during an interglacial like the present. Okay? But this is the kind of cyclicity we see. This is like Al Gore's curve, although he took it back a couple more interglacial periods. His was a CO2 curve. Ours is a sea level curve, but they record the same glacial interglacial cycles. Okay? So this is when our marine terraces formed here in California that we see. And this is the way they'd be reflected from that sea level record. This is the same graph I just showed. And then this is our landscape that we're looking at. We get this kind of a stair-step landscape where our present wave-cut bench, like the one we saw there in San Pedro, is forming during the present interglacial. The next terrace up is the one that formed during the last interglacial, right here. And the next one up during the previous interglacial, and so on. So this is the kind of stair-step sort of sequence we see on the California coast, and the Oregon coast as well, the Chilean and Peruvian coasts. A lot of coastlines around the world where the active uplift is taking place. So we'll explore that in more detail here. So let's take a look at where we see that on our islands, Channel Islands National Park. And what we'll start with is the farthest islands to the northwest. We'll work our way east and south. Whoops. And show you what we've come up with. I thought I'd start that way with San Miguel Island because we were just there this last week. And we had a good look at this marine terrace right over here, which is the last interglacial marine terrace. And its shoreline angle is actually buried under a lot of landslide deposits and stream deposits and dune sand and all kinds of things here that are kind of covering it up. But you can still see a terrace-like form there. And back in those canyons, if you go all the way in there and find the innermost part of the bench, it has an elevation of about 21 meters. And we've found corals in there that we've dated to around 120,000 years old. But there are higher terraces as well. Here's one up here, almost covered up by these dunes. But you can see a cliff up here and sort of a flattish area, and a flatter area here, and a flatter area here. These are all marine terraces as well. If you look up close to any one of those, this is the one, the lowest one, the last interglacial one. Here are the volcanic rocks that form the bedrock in that part of the island. The wave-cut bench is right along there where those arrows are pointing. These are the marine deposits that were left behind, sands, gravels, and a lot of fossils. And then it gets covered over by a lot of these stream deposits that you see here, this reddish and brownish stuff, which makes it difficult to map and try to find a lot of exposures for these things until we walk into some of these canyons like this. So we do a lot of walking through canyons to find these kinds of exposures. Okay. Santa Rosa Island, it's got a beautiful set of terraces. Here's the one that we think dates to the last interglacial, probably the 120,000, or possibly one that was during a sort of a last gasp of the last interglacial about 80,000 years ago. Down here, and again, it's covered up by a lot of stuff, but you can see a terrace form. But up on top here at about 128 meters, we've got another terrace up higher. And there's San Miguel in the background for reference. It's on the northwest coast. If you've, and I'm sure many of you have, you've taken an IPCO boat ride out to Santa Cruz Island, you're greeted by Cavern Point, which is this point right through here, and this big flat landform, that's a marine terrace. And this is one of the ones that we just resampled yesterday. We have fewer marine terraces on Santa Cruz Island, and I'll talk a little bit about why that's so, and it'll be apparent to you before too long here. Our littlest islands have some of the neatest history of all. These guys are only a square kilometer or so. Actually, I guess they're a square mile, but not much more than a square kilometer, I guess. Small islands, but look at, you've got these flat surfaces here, and up here, and over here, and over here. These are all marine terraces, those stair-step landforms, okay? Santa Barbara Island and Anacapa Island are mostly marine terraces, okay? Most of that landscape. If you cruise along Middle Anacapa, you can see two of them. A low terrace right here, which is, I guess, sometimes referred to affectionately as cow pie rock. I have heard that term. But that's the stuff that covers it up, okay? So we don't like those. Yeah. But there's another terrace right in here, as you can see. There's a flat surface. It's covered up with other stuff here that has no apparent source anymore. A lot of that island's been eroded away. But that's a wave-cut bench. Okay, so we've got two marine terraces. And this actually defines and has controlled the landscape evolution of both Middle and East Anacapa Islands. That's why they're so flat-top. They're marine terraces. Santa Barbara Island's got at least 3, and I think maybe 4 or 5 marine terraces. The most prominent ones, and I've mapped here the inner edge of them. This one's just barely visible. Got another one here at about 50 meters. Got one here much higher. And over on the other side, there is the same terrace, but the other shoreline. So the island at one time looked like that, okay, outlined by green. Okay. This low terrace down here is the one that the sea lions haul up on. And Dan Richards with the Park Service has been very helpful in getting us to understand what's going on here on Santa Barbara Island, because he studies the modern marine invertebrates out on those islands that we're studying the fossil forms of. Here they are, the lower two ones. This is the 7 and 9 meter terrace, that low one that I showed in the previous slide in red. You can barely put it on a map, but you can sure see it on the landscape right here. Okay? And then the 50 meter terrace is up here. That's the one the campground's on, and that the up there, the ranger building and research building and all of those. And we've got some higher ones as well. San Nicolas Island. If you go over on a day when there isn't a missile launch, you can go over to the west side here. And there are a series of terraces. There's a low one way down here. The big, broad one dates to the last interglacial, like on a lot of our other islands, right along through here. And that's what this road is built on, and the archaeology research station here. There's fragments of a third terrace in here. There's a fourth terrace that I didn't mark that's right in about here, and a fifth terrace, which is a very broad one, up through here. And then the creme de la creme for geomorphologists is San Clemente Island, which is absolutely the most. And who's in favor of making a Channel Islands National Park? Raise your hand. Yeah. Anybody with the U.S. Navy here? They're not in favor of it. But they're very nice about letting us get out there and do research, and they've been wonderful to us. Working out there. And I'll show you 3 of them that we found fossils on at about 21 meters, 180 meters, and way up high here at about 260 meters. But there are many of them in between. The problem we've had on San Clemente is we have had a lot of trouble finding fossils on these terraces. On San Nicolas, we find fossils everywhere, but the terraces are all covered up. On San Clemente, they're not covered up, but no. But we did find some. And then our 9th Channel Island, the Palos Verdes Hills, and I apologize for the quality of this photo. It's not the best. But here's the modern wave-cut bench. The northwest from the Point Fermin and White's Point areas, Point Fermin area actually. And you can see a series of terraces up through here going all the way up to San Pedro Hill, the very top of the Palos Verdes Hills. They're mapped by Wendell Woodring in the 20s and 30s. Incredible study, really a class. It was published in 1946 as a USGS publication, as a matter of fact. He worked so hard on this that he didn't have good topographic maps, so he made his own. He plane tabled the whole peninsula by hand. So he really did an amazing job. So, and here's Terrace 13. If you've ever driven up Crest Road, just before you get to the very top, you can find just a few remnants of that terrace up through there in someone's backyard. So we took this picture. Okay. For our young marine terraces, those that are less than about 500,000 years old, our preferred method of dating is uranium series methods on fossil corals. And you say, well, corals, well, California doesn't have corals. Well, actually we do. We have the little orange cup coral. Here they are growing in a modern setting. This is what they look like in fossil form on Nicolas Island. And I won't go into the details of this, but suffice to say that corals are the only organism that takes up uranium from seawater when they grow. We don't know why they do, but they do for whatever reason. And that uranium decays over time to thorium-230. We can measure that ratio and get an age. And that'll take us back about 500,000 years. So most of our last interglacial marine terraces, the ones that date to about 120,000 years ago, really precise ages. Problem is, poops out about 500,000 years. And we just can't measure it as significantly different from an equilibrium value of 1. So we're out of luck there. However, when that poops out, another technique kicks in. And for this one, we don't need corals. All we need is any kind of fossil shell material that's made out of calcium carbonate, as long as it's well preserved. Even stuff like this, which this is a photograph of some of the fossil material that you can find after a good winter rain, as we did yesterday. After all the rains that have occurred this winter, a lot of fossil shells appeared, just like this, which was taken in a previous year, up near Cavern Point. And you can see old mussel shells here, and glycymerus shells, and other sorts of materials. And all we need are shells of some kind for this technique. It can be even barnacles or sea urchins or anything like that. Any kind of marine organism made of calcium carbonate. And what we do is we use something called strontium isotopes. And strontium is a metal that is very similar chemically to calcium. So it has the same kind of charge in ionic form, about the same kind of ionic radius. So it substitutes for calcium in most things made out of calcium. So in minerals that are composed of calcium, marine organisms which are composed of calcium carbonate, there's always a little bit of strontium, trace amounts of it, probably even some in tons, I'm guessing. I haven't measured it, but I'm not sure, but I wouldn't be surprised. At any rate, trace amounts of it are found in marine organisms for sure. And that is because strontium is abundant in seawater. It behaves, that's what marine organisms precipitate their shells from. They have to have calcium, and it's present in seawater. Abundance of strontium. In fact, we don't even really care how much strontium is in there as long as it's a measurable amount. In fact, we don't even care about strontium-84, and we don't care about strontium-88. These are the two we're most concerned about, and they're the ones that have sort of a medium level of abundance. But the reason why is that strontium-87 is the decay product of rubidium-87. Rubidium is another trace element that substitutes largely for potassium. Don't worry about that, but that's, in case you're curious, that's what it does. So rubidium decays away to strontium as this reaction here, and this is how we've dated a lot of our old rocks in the earth, okay, using this technique. But what's interesting about this is that young rocks then, as rubidium decays, are going to have relatively high amounts of rubidium-87, low amounts of strontium-87, because they're young and not too much of this has decayed to this. So the amount of 87 compared to this other isotope of strontium, is also going to be relatively low. The amount of strontium we have here, strontium-86, is the same as what we've had since the Earth began. Okay, it's a primordial element or isotope. We have the same amount that we had in terms of numbers of atoms, just what we started out with. It's not radiogenic. That is, it didn't form by radioactive decay. But strontium-87 does form by radioactive decay. So through time, we're keeping the same amount of this, and this, and this, but we're always increasing the amount of strontium-87 as rubidium-87 decays. So young rocks then are going to have high rubidium-strontium ratios, and low strontium-87 to 86 ratios. And old rocks that have been sitting around for a long time are going to have lost a lot of their rubidium, but they'll have gained a lot of strontium-87, and they will have higher strontium-87-86 ratios. Everybody still with me? Everybody's still awake? I heard a couple of no's. I don't blame you. Hang in there, okay? We're almost done. Okay, so where do all those things come from? Okay, well, we said young rocks have low strontium ratios. Old rocks have high strontium ratios, okay? Our old rocks are on the continents, okay? So they have high strontium ratios, okay? Our young rocks are the ones that are at the spreading centers, like the Mid-Atlantic Ridge and the East Pacific Rise, and all of these spreading centers where new tectonic plate material is forming. Those are young rocks that are just coming out of the mantle, okay? So if most of our strontium input during some parts of geologic time comes from these spreading center sources, the strontium that enters seawater is going to have low strontium ratios, right? Okay, because it's coming from young rocks. However, during other geologic time periods, say for example glacial periods, when there's a lot of erosion on the landscape by ice, and then interglacial periods that follow glacial periods when the ice recedes and all this fresh glacial material is left, streams and wind and all kinds of things carry it into the ocean, you get a lot of high strontium inputs to the ocean, okay? So, what did we say about the Quaternary? Last 2.6 million years or so, a series of glacials and interglacials. So we scrape these continents, and then we recede the ice, and the wind, and the water, and everything blows it into the ocean. So is the Quaternary going to have relatively high strontium inputs, high strontium isotopic ratio inputs? Yes, indeed. So what has happened then is through geologic time, there's that MA again, okay? So this is present time here, going back to 3 million years. Quaternary starts here at about 2.6, and here's the strontium-87-86 ratio. Look what it's doing. It's going up like this, okay? That's the good news. The bad news is it changes out here in the 6th decimal place, okay? So that means you've got to have really good mass spectrometers. And we just had a power outage at the Federal Center last weekend, and we thought we might have even gotten shut down, in which case we would have had a power outage for sure. And it turns out mass spectrometers don't like power outages, and they tend to get really squirrely, and so getting that 6th decimal place is really tricky. So frequently when we analyze a fossil, to put it on this curve somewhere, we got to analyze a lot of them and see what that central tendency is. It takes a lot of work, and we've analyzed a single deposit sometimes with as many as 100 analyses just to try to get it to center in on one zone here where we can drop down and figure out the age, okay? I say this because you're going to see a very few red dots on the next series of curves, and I just want you to know what goes into those red dots, and it's a lot of work, okay? So there they are. Here's an example from San Nicolas Island, going from one of our youngest terraces up to the top of the island. Each one of these red dots represents somewhere between 50 and 100 mass spectrometric analyses of strontium isotopes. It's a lot of work. A lot of power outages recorded there as well. But at any rate, it falls nicely according to the way we think it should. Older terraces should have lower strontium isotope ratios, and they do. And higher terraces up at higher elevation, which are older, and younger ones that are at lower elevation have higher strontium isotope ratios. And in fact, the last interglacial terrace here on San Nicolas is indistinguishable from modern seawater. And that's one of the reasons why we use uranium series techniques to date that, because we can do it more precisely, okay? But this will show you kind of what it looks like. So it looks like our highest two terraces, which are different in elevation by a small amount, have strontium isotope ratios that are indistinguishable from one another. They're a part of the curve here where we really can't tell them apart. So we suspect they're fairly close in age. But as you can see, whatever that drops down to, just under 1.5 million years or so. Does that look about right? Something on that nature, okay? And and successively younger ages as we go up to the modern one here. On San Clemente